Hello, students. How are you? Today I'm choosing a bit of a difficult part of the electrical engineering where we study about the dynamic modeling of the system and try to design the controllers which would give the result as per our requirement. And previously, I have shown you the simple example of the DC motor where I have derived the mathematical model of the system from data, or even you can derive the system equation from the first principles using the force method or the Kirchhoff's voltage law and so that and something like that. So in this video, I'll go to a bit more difficult part where students get very confused and even find them very difficult to comprehend the overall concept. And this is the dynamic modeling simulation of the synchronous machine. Okay, I have made a short video on the synchronization of the synchronous machine on the grid, and I will do some kind of the perturbation or some kind of the changes on the machine and show you in real time also. And here I am trying to show you the process of simulating the synchronous machine connected to the grid, and how the synchronous machine will behave when certain disturbance occur in the system, like that. Okay, so without any delay, here is my synchronous machine. Like this is a synchronous machine here. A synchronous machine is basically a simple is a machine that is that generates the three-phase voltages when driven by some kind of you know external power, mechanical power, or I would say mechanical torque by some hydro turbine or some steam turbine. And when provided sufficient amount of the field or electromagnetic field or current in the field, it will generate voltage. Okay, it will generate a three-phase voltage, and the three-phase voltage is used, or the three-phase voltage or the three-phase power generated by the alternator will be fed to the grid by some kind of maybe transmission line, right? Or direct it will be connected to the grid. This is the infinite grid. Okay, this is our grid. I'd say V infinity, or simply VZ here. Now the problem is, simple problem is, it is not easy to control the whole system when some disturbance occur in the system, like maybe the transmission line may be tripped down, or some kind of fault may occur there. Okay, or maybe the prime mover could fail sometime, or there could be a problem in the governor system, or the prime mover, or there may be some kind of fault in the field system. Okay, the field can change, and when any part of the or either field or change, or the power may fluctuate, or some kind of flux fault of occur in the system, or any fault occur within the synchronous machine, maybe in the stator. And in that situation, the synchronous machine will behave in different way, which could be very dangerous also, which could lead consequences that could harm the system. So how can we develop set of the equations and try to solve those equations to obtain the characteristics of the system when any of this kind of situation occur in the system? Okay, for this we have to derive the system of equations that describe the synchronous machine, right? For that, you can go to the a lot of references that are available in the internet also, or in the books, like book by Prabhakundur, or the book by Anderson or Schaeffer. There are several textbooks that are available in the internet, where you can learn about the modeling of the synchronous machine. And there are several techniques to derive the modeling equations, and different engineers feel comfortable with some kind of the derivation and something like that. But here I want to show you something that is very easy for the engineers that are working on the industries where they got the technical data sheet of the synchronous machine, and the technical data sheet of the synchronous machine will give the all the parameters of the synchronous machine, like the transient reactance or the subtransient reactance, something like xt, xq, right, xd dash, xq dash, and even the time constants, direct axis time constant, and quadratic axis time constants. These types of parameters are available in the available for the particular synchronous machine that is used for the study, or which would be your the purpose of the study. Okay, so this is the basic idea. Okay, so I'm very much trying to simplifying the overall concept. Okay, so previously I have shown that the dynamics of the system are represented by the differential equations and some algebraic equations. So for the machine, the dynamic equation and the algebraic equation can be described, can be written as like this. Okay, this is the fourth order model of the synchronous machine, and this fourth order model of the synchronous machine discuss about the or the encompasses swing equations, uh, power angle equation, transient axis, voltage equation. Okay, so this is the fourth order differential equation with three algebraic equation, and we have to solve this equation for the particular operating condition, or the for the particular steady state condition with some disturbance occurring after that steady state condition. So first we have to determine the steady state condition, and second, after determining the steady state condition or the point of equilibrium point, then we add some kind of perturbation there. I mean, let's say this machine is running at some speed, okay, fixed speed, and the field voltage is constant, something like that 1.2 pu. This is running at 1 pu, and it is generating some voltage, fixed voltage, which is equal to maybe at that scenario it's equal to the grid voltage, but it has some kind of delta angle phase difference between the grid voltage and the synchronous machine voltage. And these are the initial condition. Okay, machine is running continuously running, right? Machine is continuous. This is the steady state point. Now at any particular point, at any particular time, some disturbance occur here. Maybe the governor failed, or the excitation system failed, or some fault occur, or something, and anything like that. Okay, after that, the let's say if this is the graph of the omega, the speed will change. Okay, the speed will change, and if the system is stable, if the system is stable, it will oscillate for some time and reach to some steady state point after that disturbance is removed, or another steady state point is reached, or in overall language, the system will be stable. But if the case is unstable, then the system will go, okay, unstable, or the system will lose synchronism, and something bad happens here. Okay, I think you have understand about the initial condition. You have to determine the initial condition for the solution of the system. So for developing the initial conditions, you just write the equation in form of the algebraic form. You keep this 0, this is 0, this is 0, this is 0, and solve that algebraic equation and determine the initial values. Okay, that is the finding the point of the linearization. And here I have written the algebraic equation, and I solved that equation and determined the initial value here. Okay, and after getting that initial condition or the initial values, this is the initial values. Okay, this is the initial operating condition, angle, this is the initial speed, this is the direct axis internal voltage, and this is quadratic axis internal voltage. Okay, so this is the initial condition. Now I want to add some I want to put some kind of disturbance in the system and try to observe what will system behave when that disturbance occur in the system. Okay, so for that, here these are the parameters of the system I have taken into consideration. And the system of equation I have written here. Okay, this is the state variable, and this is the algebraic equation, this is the torque equation, and these are the fourth order differential equation, right? The fourth order differential equations and then used to uh, solve the system. So if I kept the initial condition as usual, then system will behave as normal. Okay, but if I put some kind of disturbance here, for example, if the speed is changed a bit like this, okay, due to the governor or some kind of prime mover problem, the speed just changed by some speed in speed, then what will happen in the system? If I want to check that, then I will use this initial condition. Okay, and this is my differential equation representing the dynamics of the system, and I use that equation and solve it. Okay, and I plot the omega of the system. So initially, mm, initially the speed of this synchronous machine was 1, but at 0 time I put an initial condition of 1 plus 0.25, that is 1.25, and it will start from the 1.25. But you know, in synchronous machine the speed cannot be changed, right? The speed has to be constant because it's by name it is a synchronous machine. So the synchronous machine will react, okay, will react, and it try to balance the speed at the 1 pu. How will it balance the 1 pu? Maybe it will supply some power to the grid, like something like that. So this describes the dynamic nature of the synchronous machine when some kind of speed will change in the system. Okay, so if I continue with the initial value here, with some initial value here, then sorry, so I have to run out for this, some kind of initial value, then the this is very small value, 1 e to the power minus 5, so it is not changing at all. But when I add some small amount of the disturbance, like if I change the power angle, if I change the power angle by some value, let's say 0.1, this is the perturbation, and it will, sorry, I have to run on for this because I have a lot of variable defining here. So when I changed by some value, okay, when I changed the some value by the delta, that means I add some disturbance in the system will react in something like this. Okay, so this is the nonlinear solving solution of the system of equation of the synchronous machine. But in reality, this system is nonlinear, and we cannot design the controllers, or we cannot develop appropriate control system in nonlinear system directly using the nonlinear equations. So for that we have to linearize the nonlinear equation in some equilibrium point. So what would be our equilibrium point? Our equilibrium point will be our initial condition, right? That initial condition will be our equilibrium point, and that equilibrium, around that equilibrium point, we will linearize the system. We'll develop the linear model, and we'll solve the linear model, or we'll use the model control theory, that is ABCD. We develop the ABCD matrix and determine the eigenvalues, or design some kind of control system, like developing the governors, designing the automatic voltage regulator, and so on. So this is a very basic concept on the modeling and simulation of the synchronous machine, and I have mentioned you, shown you the system equation representing that machine, and I am using the fourth order equation, but there are still better models like sixth order equations, which also incorporate the transients in the damper windings and other associated windings of the synchronous machine. So this is all for this, and if there is any questions to you, you can directly contact me or directly email me on this context. So previously I have made videos on the PSAT and PSAT software, which basically solves the differential equations uh, related to the dynamics of the system. And in the very foundation, the computer softwares are performing this kind of the initialization, this kind of the solution of the differential and algebraic equation in their inner algorithm. So this is the very basic concept for now. Thank you for this. Okay, if there is any question, please you can just email me or something like that. Okay, thank you.